and start recording. And here we go. All right, so what we are watching is an animation of what it would look like if you started at the sun and just started rocketing away from it at the speed of light. This video's, like I said, it's going to last for 45 minutes, so we're not going to get halfway through the solar system. The solar system is ridiculously huge, but every time we pass something, then that's going to be the new topic of conversation. So we got the sun here. The sun is 99% the mass of the solar system. It's absolutely huge. By the way, you'll notice, depending on where we are in the screen, in this top right corner, it says next celestial object, and then it says its name. If the faces and stuff are in the way, you can just move that out of the way, because you'll see that it says Mercury is coming up in a little over 2 minutes. So that means we got about 2 minutes to talk about the sun. Okay, so I may have mentioned this before. I say this in like almost every science class, but all these, celestial objects, they're named after mythological figures, like Roman mythology. And the Roman god of the sun is Helios. So that being said, the element of helium was first observed by some of its atomic properties that you can see by light in the sun. So helium is like literally named after the sun, because that's where it was first known to exist. Helium and hydrogen are pretty much all of the sun, and the way that the sun works is it's just a big fusion machine, right? So like I said, it's 99% the mass of the solar system. It's just ridiculously huge. And so there's so much gravity that the pressure from, just a solar system's worth of mass around the core is enough to force hydrogen atoms together, and the nuclei fuse into a helium atom. That nuclear reaction is what drives this sustained nuclear explosion. So really what makes a star is just when you have enough hydrogen in one place that the gravitational pressure is enough to force the atoms to fuse. That fusion reaction releases so much energy that you've got this balancing act between, a massive nuclear explosion outward and then massive gravitational collapse inward. And depending on how hot the fuel is burning, it's going to determine the size of the star. Right now, our sun is what's called a main sequence star, which basically means it's in the prime of its life. It's like 4.5 billion years old. In another couple billion of years, it's going to use up a lot of its hydrogen, and it's going to swell up and actually become a red giant, at which point it will incinerate all the inner planets. And hey, there goes Mercury. We've been flying out here for 2 minutes, and it's practically already gone. So let's talk about Mercury for a bit. Mercury has no moons. Oh, by the way, I haven't been watching the chat. I don't know if there's anything going on in there. Okay.
I have a question.
Go ahead, David.
So this is moving at the speed of light.
Yes.
Well, so if we sped the video up, it'd be faster than light.
Yes. Yes, that is actually, I was, looking at the video earlier. That's one of the most highly rated comments. Yes, if you watch this at speed it up, you are going faster than light. Also, you can just skip around and teleport immediately. But that's one misconception. I don't know if misconception is exactly the right word. We tend to think of light as super duper fast, because of course it is. It's the fastest thing in the universe. And light can go around the Earth several times per second. But we also kind of forget how ridiculously huge the universe is. We've been going at the speed of light for like 3, almost 4 minutes, and we haven't even gotten to the second planet yet. Anyway, so about Mercury. So Mercury has a year that's like, what was it? It was about like 2 months long or something, like a 60-day year. And for a while, scientists thought that Mercury was what is called tidally locked, which means that it doesn't ever rotate, and the same side of it faces the sun. Turns out it's not quite true. It actually rotates like 3 times for every 2. So like it's got like 3 days per 2 years, which is really close. However, something that kind of crazy about it, we're pretty sure there's ice on Mercury. And the reason is because it has like an axial tilt of basically 0 degrees, which means it has absolutely no seasons. That also means that it has some craters near its poles, which are perpetually in shadow. So even though it's the closest planet to the sun, there are some parts of it that never see any sunlight at all. And that means that there's little places for ice to get trapped. Let's see. So we're just about to hit Venus. There was a mission to Mercury. I think it ended about like 8 years ago. And eventually the satellite just had to crash on it. All right, anyway, there goes Venus. Venus, obviously the second planet in the solar system. If you guys know cool nerdy stuff about Venus or whatever, you just throw it in the chat. I can totally talk for 45 minutes about the solar system, but like, come on, you don't want that, do you? Throw some questions or some comments in there. You know, let's make this a little interactive. Anyway, about Venus. So Venus's atmosphere is just it's ludicrous. So the atmosphere of Venus is almost entirely carbon dioxide. There are clouds. They are sulfuric acid clouds. So even if Venus were a normal temperature, that alone would kill you. You'd suffocate immediately, and that's if, you know, rain didn't dissolve you. But the atmosphere on Venus is so thick that it's something like 90 times atmospheric pressure, which is just ludicrous. Being in the air on Venus is like worse than being underwater on Earth. But the atmosphere is so thick that if it were clear, I've heard it hypothesized that light would bend around the planet, as in if you had a good enough telescope, you could just see all the way around the planet, which would drive flat earthers crazy. Although I guess they'd be flat Venusians. I don't know. So Venus is also the warmest planet. It's I got a couple people waiting. Here we go. Let them in. Venus is the warmest planet because of that greenhouse effect, which is also kind of mind-boggling because it's twice as far away from the sun as Mercury is. But you know, the greenhouse effect, it's a real deal. We're coming up. Oh, how long would it take to go all the way around the solar system? Now, when you say around the solar system, do you mean like if you could take the jogging track that Neptune takes? Is that what you mean by around? Okay, so Neptune, if you travel at the orbital speed of Neptune, it's going to take you a little more than 150 years to go around the solar system. So a year on Neptune is like that. I'll get to Earth. I mean, we're there already. But I like to point that out. It's kind of nuts because, like, if you think about like 150 years ago, that was like 1870. You guys, like, the Civil War was last year on Neptune. Anyway, if you did that at the speed of light, though, I'd have to calculate the distance. I don't actually know that one. I'd have to guess. It might be a couple hours. That would be my guess. All right, well, I'll get to Earth in just a second, but something that just came up, I want to point out that you can see the entire orbit of Mercury now. What planet do you think would be the most livable for humans? Do you mean other than Earth? I assume it's other than Earth. That's definitely Mars. Absolutely Mars. And here's the reasons why. So since we're in the middle of Earth, I can talk about what makes Earth livable. And then Mars is next, so we can get to that. So Earth occupies what's called a Goldilocks zone. I mean, you know the story of the 3 bears where, like, you know, the father's stuff was too big or too hot, and like the mother's stuff was like too soft or too cold. And then like the baby bear stuff was just right. Well, In order for life as we know it to survive, we need a couple things, right? We need like an oxygen atmosphere. We need liquid water. We need certain kinds of chemistry to be possible. And if you're thinking about it in terms of chemistry, you need the right ingredients and you need the right like temperature. Earth happens to be in this zone that is far enough away from the sun that everything doesn't just get like totally destroyed by radiation and by heat, but also not so far away that water can never be in a liquid state. When you get to chemistry, almost all the chemistry that you do has to be mixed in water because of some important properties that water has. So Earth is in a place where you can have liquid water. And it's a combination of its atmosphere, but also its temperature. Earth is also important in terms of life because of the chemical ingredients that are there. Now, most of the terrestrial planets are kind of all made of the same stuff anyway. So if Mars had had a history of evolution like Earth has had, then it could possibly support life. But there are some crucial differences. I want to tell you those differences as soon as we get to Mars, though, because I still have a minute or so before we get to Mars. I want to say a couple things about Earth. So Earth is the first planet to have a moon. Now, I mentioned something in the awful video I suggested you not watch yesterday. I don't know if you got to that, but one of the hypotheses about the formation of the Earth is what's called differentiation, which means that the Earth started out as a molten mass. And when things are fluid, you know, things are able to move around inside, and denser materials tended to sink down to the core. So that's why we have like a core made like entirely almost of iron. And the lighter substances like silica, you know, were at the surface. That's why we have, you know, a lot of silica in our rocks. So the question that I posed was, okay, so all the heavy stuff is at the core. Then how come there's so many heavy metals at the surface? Why is it that we're able to mine uranium and gold? Like, why is that at the surface? Has to do with the fact that during the Earth formation, the Earth got stirred, as in there was an impact that reorganized the materials in the Earth, actually ejected a whole bunch that became the moon. And that's part of why we're able to mine stuff. Hey, there goes Mars. So how long has this been now? Like 12 minutes? Oh no, yeah, it's been like about 13 minutes. Okay, so about Mars, the differences. So this actually came up a couple months ago. You know, back when life was normal. Do you guys watch the Super Bowl? There was a Super Bowl ad where for like some sort of like it was a soda stream. That's what it was. It was something that you could make soda at home with. And it was in this ad, there were like some astronauts on Mars, and they found some liquid water. They like picked it up and took it back to base. And then like one of the guys made soda with it and drank it. It was dumb. You can't have liquid water on Mars. And I don't mean if it were only warmer. No, it's actually the air pressure as well. See, the air pressure on Mars is so low that when water rises up to 0 degrees Celsius, like freezing temperature, the molecules actually have enough energy to leap out and join the air. There's not enough air pressure to keep it from evaporating. When you get to chemistry, you're going to learn something called a phase diagram. It's basically the conditions under which different substances will be liquids, solids, or gases. Mars is kind of close to what's called the triple point, which means that water is so close to being a gas, a liquid, and ice all at the same time. So you really can't even have liquid water on Mars. If you wanted to make Mars livable, you're going to need to increase the air pressure because life requires the ability to absorb gases from the atmosphere. You're also going to need some oxygen. The atmosphere of Mars is almost entirely carbon dioxide. The temperature is actually not that bad. Mars is at the edge of the Goldilocks zone. The warmest temperatures on Mars are warmer than the coldest temperatures on Earth. There is a little bit of an overlap. So if you could change the atmosphere of Mars, you could kind of turn it into one big red Antarctica. But there's problems with that. Mars is smaller than Earth, which means that it doesn't have enough gravity to keep that atmosphere. So you'd have to like build an Earth habitat for yourself on Mars, but it wouldn't be that far. I think the day of Mars is like 24 hours and like 20 minutes or like 30 minutes. It's very, very close. Okay, the warmest planet, that is definitely Venus. You'd think it might be Mercury because it's closer, but because Mercury has no atmosphere, then it just gets baked on one side and then the heat re-radiates off of it. Venus is the warmest because it retains that heat. Now, maybe I should qualify that because Venus has the warmest surface. However, the cores of planets have different temperatures. For example, you know that like magma underneath the crust can be thousands of degrees Celsius. That's way above the surface of Venus. So if we're just talking about the surface, then Venus is the warmest surface. But if you wanted to find the warmest temperature in a planet, I think it would actually be Jupiter. The core of Jupiter is, I'm just pulling this off the top of my head, but I believe the core of Jupiter is like 30,000 degrees. And the reason for that is because of all the intense pressure. Speaking of Jupiter, we've been through Mercury, Venus, Earth, Mars. The next planet is Jupiter. That's actually going to be the last planet that we see here today because the solar system is so ridiculously huge. You guys know in the solar system what you find between Mars and Jupiter, what we should be in right now? If anybody knows that, throw it in the chat. Anyone want to take a guess at this? Oh, well, there goes the label. Never mind, I gave it away. So the approximate beginning of the asteroid belt. So I don't know about you, but when I was growing up, the impression that I got of asteroids came entirely from The Empire Strikes Back. Surely you all know The Empire Strikes Back, you know, episode 5 of the Star Wars saga. And you know the scene where like the Millennium Falcons, you know, getting away from wherever, and they go into the asteroid field. Yeah, I got him. Thank you for that. And you know, it's the one where like they're inside the big space worm and they just get out. So they're in this asteroid field, and all the asteroids are like really close together. They're all like hitting each other and, you know, breaking off. That's what I thought of, like asteroid fields. Guys, we're in the asteroid belt right now. Do you see anything? Right. So remember, at this scale, even large things like planets are tiny. At this scale, the asteroid belt is so spread out that it's not like, you know, this really dense collection of rocks, like, you know, like rocks on a beach or something. It's more like if you took a handful of sand and just scattered it across the table. That's the asteroid belt. Okay, well, since we have all this time, let's see, we've got, I'm actually not sure how much time we have left. Okay, but we might have like 25 or 30 minutes. No, probably 25 minutes left. So I have to spend this time talking about each of the gas giants. Why do galaxies look stupid? Why do galaxies look stationary when scientists say they rotate? That is an excellent question. So yesterday's homework. I noticed a lot of you did that. Good job on that, by the way. Hey, there's Vesta. Bye-bye, Vesta. There was a relationship between the distance from the sun and its orbital period. Remember that? The closer planets orbit more quickly, and the further planets take longer to orbit. Like Mercury goes around the sun every like 60 something days. Venus goes around the sun every like 200 something days. Earth goes around the sun every 300 something days. Mars goes around the sun every 600 something days. The further out you are, the longer it takes you to rotate. So galaxies are tens of thousands of light years across, which means that the stars on the outside take hundreds of millions of years to go all the way around, right? Like our galaxy has not had one complete rotation since the human race evolved. It's probably had one since the dinosaurs. That's how slow it is. Now, you know how our galaxy is a spiral galaxy, right? You know, it's got like here's my high-tech graphics. How do I, yeah, spiral galaxy. It's got like the spiral arms. So the reason we have spiral arms is because the things on the inside near the galactic core are orbiting faster than the things on the outside. In other words, the things on the outside of the galaxy are trailing behind the things near the center. So you can actually estimate the age of a galaxy by its spiral arms. All that to say, galaxies are huge. So their orbital periods are enormous. They're orbiting very, very slowly. Now here's a question for you, because this is something, hey, there's the orbit of Earth. This is something that comes up a lot when it comes to astronomical data. So stars live for billions of years. Galaxies rotate over hundreds of millions of years. If the human race has only existed for, say, 100,000 years, which is a tiny fraction of both of those numbers, and we've only been doing science for like 400 years, which is an even tinier fraction, and we've only been doing astronomy properly for like 100 years, how do we know about these processes that take billions or hundreds of millions of years if we can never see them from start to finish? I want to give you like kind of an analogy for that. Let's say you were to walk through a housing development and you see houses in various stages of construction. Like you go to one house and you can just see like a foundation that's dug out of the ground, maybe like some concrete poured in there, but not much, just a big hole in the ground. Then you go to another house and you can see that there's a frame built, right? And you go to another house and it's like a frame and some walls, but like the insulation is still there. There's no windows. Then you go to another house and it's mostly finished, except like the ground is still all covered in dirt because, you know, the grass hasn't been planted yet. If you're able to see a long process in various stages, you're able to build a model of how it should work that matches all those different stages, then you don't actually have to see the whole thing from start to finish. We can see stars in the process of forming. We can see stars like our star, our sun, that's like in the middle of its life. We can see stars that are near the end of its life, like Betelgeuse. It's that star in the Orion constellation that it was like starting to get dim, and scientists were like, oh, it might go nova, it might go nova. And like, you know, soon means maybe in 10,000 years. So yeah, despite them taking like forever, we can get ideas of these super duper long processes. What does a forming star look like? That is an awesome question. So part of chapter 27 has to do with what's called the Nebular Hypothesis, which is a hypothesis for the formation of a solar system. So here's how this works, okay? You just have to have a huge cloud of gas and dust. Those are nebula. We see nebulas all over the universe. In fact, there are some nebula that you can see with your naked eye. The Orion Nebula looks like a star in the constellation Orion, it's actually a nebula. And if you just get like a nice pair of binoculars, you can even see it's too fuzzy to be a star. But in those enormous clouds, gravity is a force that, you know, stretches across like all space, and under gravity, enough mass in one place will tend to collect together. Now, as it tends to collect together, two things happen. One, more mass in one place means that the gravity is more concentrated, and so it all kind of falls in and collapses. Something else that it does, though, is that the pressure increases. Now, increasing pressure can also mean increasing temperature, which tends to make gases expand. However, this is able to radiate that heat out, and so it tends to collapse. When that happens, what you end up with is a cloud of gas that collects so much mass in the one place that the pressure causes a fusion reaction like we have in the core of our sun. When that happens, basically what you're going to see is a spot in a nebula that just becomes bright. But remember what I said about super duper long processes, right? This is the kind of thing that would take millions of years to happen. So if you were to ask, what does it look like on a human time scale, it just looks like a photograph. If you could do a time lapse over like, you know, a million years or something, it should look like an explosion in reverse, where if you think explosion, it's like bright flash and then just spread out. Well, in reverse, it would be, and then a bright star at the center. That is what we'd expect it to look like. Of course, it's also happening in a nebula, so it's kind of like behind a cloud as well. I see Jupiter is in 16 minutes. We've got 4 planets out there, so I'm going to see if I can't spend about 4 minutes talking about each of these outer planets. By the time we get out there, then our class will be done. Jupiter is huge. Jupiter is the largest planet in the solar system. You didn't need me to tell you that. However, there are some things about Jupiter that not everybody knows. First of all, Saturn gets all the credit for having rings. Jupiter also has a ring. It's just a lot smaller by comparison, so it's kind of like, you know, not that big of a deal. Jupiter also has like a ridiculous number of moons. The number keeps changing, so like the number that I learned as a kid, like there are just dozens and dozens of moons. However, there are a couple things about Jupiter that make it really important, not just like, you know, because learning about science is important, but also like for us. So Jupiter has an enormous magnetic field. And the reason that it has an enormous magnetic field is similar to the reason why the Earth has a magnetic field. The Earth has a magnetic field because we have an iron core. And iron being a magnetic material, when that iron core spins, it has what's called a dynamo effect. And it basically turns the Earth into an electromagnet. What Jupiter has is a form of hydrogen that's called metallic hydrogen. And the way that this works is the pressure and temperature of that space inside of Jupiter is such that the hydrogen tends to act more as a metal than a non-metal. And I'm pretty sure I'm getting this right. The metallic hydrogen produces an electric field, a magnetic field, similar to how Earth's core does. So yeah, Jupiter's magnetic field is enormous. The other field, and this is one that's important for us, is its gravitational field. Because, like I said, Jupiter's enormous. The sun is like 99% of the mass of the solar system. Jupiter's 1% the mass of the solar system. Just for a second, just worth pointing out, if you didn't have that timer going on, would you even be able to tell this video is moving? We're moving at the speed of light, you guys. Okay, anyway, so Jupiter's gravitational field, so huge. This is actually vital for our survival on Earth, and here's why. Because Jupiter's orbit is outside of the Earth's, if there were any, say, large asteroid just drifting through the universe, that happened to pass through our solar system. If it were to hit one of the terrestrial planets, it would destroy it, or at least it would transform it so much that no one would survive. I see your question about least habitable planet. I'll get to that in just a second. Because Jupiter is so large and outside the orbit of the Earth, it means that anything entering the solar system is going to end up hitting Jupiter instead. And in fact, this happened when I was a kid. It was in the 90s. There was a comet that actually hit Jupiter. You can find pictures of it. I think it was called the Shoemaker-Levy comet, and it just like crashed into Jupiter. If that had crashed into Earth, we'd all be dead. So Jupiter basically catches all that. All right, let's see. Earth is flat. Well, this video is fake, but not because the Earth is flat. What is the least habitable planet? So I think all of the gas giants are going to tie for that because there's nowhere to stand. I wanna find links for these and send them to you. There's a couple of videos on YouTube that ask what would it look like to fall into Jupiter, or like what would it look like to fall into Saturn. They're absolute nightmares. Absolute nightmares. I'm not quite sure what you think of, like just being in the middle of the deep dark ocean. Just imagine being in an entire planet of it. What happens when two black holes collide? That question is awesome. Did you know that's happened? Okay, it was neutron stars, but that happened in was it 2011? I think it was 2011 or 2012. No, I'm sorry. I'm thinking of the wrong year. No, that was the Higgs boson. I think it was 2014. So there are these telescopes. I think one's in Arizona. I can't remember where the other one is. It's LIGO. It's a laser interferometry telescope for detecting gravitational waves. A couple of years ago, it detected some gravitational waves which came from two neutron stars colliding. Neutron stars are close to black holes or not quite. So what happens is the two neutron stars orbit each other, and then as they get closer, they orbit each other faster until they just spiral down and collide with each other. And what happens is you get a gravitational wave, which is a ripple in space, which is, how the heck do I explain this? How does one explain this? Tell you what, I'll try and relate it to the solar system, and then I'll move on to Saturn. So one of the things that led to the discovery that Isaac Newton didn't get gravity completely right was actually Mercury. Isaac Newton's theory of gravity was excellent, and it permitted people to like make all kinds of explanations about the orbits of planets. There's one planet that Newton's gravity couldn't explain, and it was Mercury. Now, it was so close. Like, we're talking like it would be correct for a decade. But you know how, like, if you got two clocks that aren't quite perfect, one of them will end up fast and the other one will end up slow. Newton's gravity was so close for Mercury, but it was like off by like a degree a century, or some ridiculously tiny error like that. But at least it was enough to show that Newton wasn't quite correct. Turns out that the idea where gravity is bending space is what explains it better, because Mercury being so close to the sun means that it kind of gets dragged through the dip in space that the sun makes. All that to say, when you get two black holes or two neutron stars or whatever, they each are making a dip in space. When that merges, then it has the effect of, similar to like how when you like shake out a sheet or something, where like the ripple travels through it. That happens through space, but it's the bend that's caused by gravity. I just can't do it justice, a face and a voice in a box. Okay, well, let's talk about Saturn real quick. Saturn is the least dense planet. It's actually less dense than water. You know, kids' science shows will say, like, if you put Saturn in a big bathtub, it would float, forgetting that, you know, if you had a bathtub large enough to hold Saturn, it would just be its own water planet. Anyway, yeah, so everybody knows Saturn because of its rings, fabulous, gorgeous rings. Um, and I was talking about rings earlier, where there are some moons that keep it stable. Other planets do have rings. What's special about Saturn's is that they're the largest and they're the most complex. Now, I also mentioned that everything in nature is kind of a balancing act, right? Like the sun is a balance between the nuclear explosion and the gravitational compression. All the orbits are balances between falling into the sun and flying away. Well, the ring is in a balance as well. And like all balances, it won't last forever. The rings, I mean, eventually will go away, but it's going to take an astronomical amount of time. Saturn has these hexagon-shaped cloud patterns around its poles, which are really fabulous. If you ever look up pictures, you might see them. But I gotta move on because we've only got like 7 minutes left in this, and I've got 2 more planets. Okay, the next planet is another crazy one, and that's the planet Uranus. So Venus and Uranus both have really odd orbits. So the sun rises in the east on the Earth because that's the direction that the Earth rotates. Venus orbits rotates the opposite way. Uranus has its axis like almost completely on its side. That's very, very unusual. And I think this is something that everybody knows, or at least it's pretty widely known, because every time you see a picture of the planets, Uranus is the one that's on its side. Because of this, I want you to imagine what seasons would be like. Okay, so like on the Earth, right? So you got your seasons. So that in the northern hemisphere, summer. Here's the sun, right? In the northern hemisphere, summer, when the axis is tilted towards the sun, then the northern hemisphere gets more sunlight, and the southern hemisphere gets less sunlight. And it's the opposite in winter. What if the axis was like this? So basically, what would happen is the equator would have a perpetual sunset or sunrise. It would just always be on the horizon. During one part of the year, the North Pole would just be in the sun all the time. During the other part of the year, the South Pole would be in the sun all the time. It almost flips equatorial and polar weather just completely around. Okay, so there's Uranus, now Neptune. Neptune is now considered to be the last planet in the solar system. It's really awkward using the textbook to do this chapter because it was, it was published like a number of years ago, and it was back when Pluto being demoted was like fresh news. So it keeps talking about Pluto like it's a planet, but maybe not. And at this point, like nobody even mentions Pluto anymore, which is kind of sad. So Neptune, now considered to be the last planet, so that there's 8. Neptune has the fastest winds in the solar system, also the lowest temperatures, and it is blue due to, I think it was methane, and that blue color is why they named it after the god of the sea. What is planet X? So I can hopefully explain what planet X is in part of the story of Neptune. So I mentioned how Newton's theory of gravity was like it for a while. It was developed in the early 1700s, and it was basically untouched until the early 1900s. So like it was the predominant theory for 200 years. It was that good, and it's so good that we still teach it. We just say, by the way, it doesn't work near black holes and at the speed of light. But after the planet Uranus was discovered and its orbit was predicted or described using Newton's theory of gravity, turns out that the actual orbit of Uranus didn't match the prediction based on Newton's theory of gravity. So there was like two options. Okay, the theory's wrong because it couldn't describe the orbit, or there's something we're not seeing. They were so confident in Isaac Newton's theory of gravity that they went for the second one. There's something that we're not seeing. They're actually able to hypothesize the reason that Uranus's orbit is off is because the gravity of another planet is affecting it. They're able to calculate where this planet should be in order to cause this effect. So they just pointed a telescope and looked, and there it was. That's how Neptune was discovered. So when it comes to other planets, for example, planet X, the only reason to think that it is there is because if it were there, it would explain something that we haven't explained yet. I am currently not aware of what planet X is supposed to explain. So here's the deal with science. There's this principle of explanation called Occam's razor. I'm going to write that in the chat just so that you can look it up if you ever care to. Called Occam's razor. William of Occam was like a philosopher in some time, I don't know, and he basically gave us a rule for how to determine if an explanation is good. You want to avoid suggesting explanations like that are more complex than you actually need. Okay, and so if you're able to explain the motion of a planet with gravity, then just do that. If you could explain the motion of a planet with gravity and also with astrology, but the gravity does it without astrology's help, just get the astrology out because you don't need it. If there is some phenomenon which we don't know what's going on with it yet, it is possible to suggest maybe there's another planet like we did with Neptune, but that's only appropriate if that's the best explanation and not if gravity can't do it by itself. But like I said, I don't actually know what planet X is supposed to be explaining. Okay, we are less than a minute from Jupiter. So at this point, I'm going to start to tie it up. After this would be Saturn. So if we got to the end of this video and then waited for Saturn, we'd be waiting for half an hour. We wouldn't get to Neptune for about 4 hours. Our solar system, from the sun to Neptune, is 4 light hours. So, you know, that would be like to the end of the school day. And if you wanted to wait till the end of the school day, I suppose you could. But obviously we're not going to do that, and the video doesn't go that far. Here are Jupiter's moons. Here's Jupiter. How lovely. All right, so those are the 4 largest moons of Jupiter. See Jupiter. All right, so as you can see, Saturn is in 35 minutes. The video is actually about to end, so we're not going to go there. But the yeah, like that's the video. So Saturn, half an hour. Neptune is several hours away. Do you know how far away the next star is? If you wanted to wait until we got to the nearest star at the speed of light, it would actually take you until you graduated from high school. That is 4 light years away, or a little bit more than 4. Anyway, that was the 45 minutes that I promised. So at this point, we can be done. I'm going to have a video posted tomorrow about the phases of the moon If you guys have any other questions, I don't mind hanging out for a couple minutes to answer them. Otherwise, y'all can just head out. Oh, we got a couple. What's the assignment for today? So it turns out that the assignment I was thinking of giving for today, I actually just gave yesterday. So none, no assignment. Thank you for asking. Let's see, I lost the chat. Here we go. Is it possible for a planet to be anything other than a sphere? That is a good question. The answer is no. So even asteroids, large asteroids, are spheres. So here's a way that you can actually picture this fairly well. So let me just I'm gonna take this square Post-it note. I'm gonna draw a circle on it. All right, so here's your round planet. If you were on a round planet, do you know what that is? That is a mountain thousands of miles tall. This mountain would weigh so many quadrillions of tons that the planet's weight couldn't support it, and it would collapse into the planet. Well, that would just round it, okay? So the way that things tend to form is everything wants to be as low energy as possible. To raise something up to the top of a mountain takes energy, which means you get less energy if it's down closer. It's actually the same reason like water drops circles or are spherical. It's because to stretch it out and give it a shape requires an investment of energy. And as long as nature's trying to like spread energy out, then you're going to end up with a round surface. That's a good question. Flat Earth, anti-vax. Do you know what that does to me? Like just because I'm a science teacher, like to see adults being flat Earth and anti-vax. I'm not very good at anti-vax stuff because that's like medicine and chemistry, and that's not what I studied. But like flat Earth, man, that's my jam.
Is it?
Go ahead.
Isn't it ironic that most anti-vaxxers are vaccinated themselves?
Is that right? Oh,
yeah,
they were vaccinated. Oh, of course they are, because all the ones that didn't get vaccinated.
Yeah, because they're alive.
Yeah. Yeah, I guess so. Yeah, like I said, the anti-vaxxers, that's one that I have a hard time with, because the subject matter with that. Oh, by the way, if you don't want to be here anymore, y'all can leave. Like,
all right, see you, nerd.
But yeah, flat Earth. That's one that that at least you can do that one just by walking outside. Oh, what does space have to do with zodiac signs? Those are based on constellations. All the different zodiac signs are constellations, and the idea is that depending on what time of year you were born, there'd be different constellations in different positions, and it would just be a superstition that what's happening in the sky has to do with happening on the earth. There's a principle of I don't know if it's exactly a religion, but it's a form of spirituality called Hermeticism. And it's got this like saying, as above, so below. It's basically like that there's different layers of reality. There's like a heaven, and then there's like a earth, and then there's like a underworld. And basically, things kind of rhyme between them. So if you can see stuff in space, in the heavens, then you can kind of know what's going on Earth. What's really funny about that, what that is that when that was all developed like thousands of years ago in Babylon, or the Babylonian Empire, the stars were in different positions, which means that like, say like, I'm a Taurus, because, my birthday just happens to fall during that time. The time frame for Taurus from April to May was different like 4,000 years ago. So, yeah.
Guys, all right, I'm making a new astrology symbols. It's called the bees. If you see dots in the sky at night, Those are called the bees. The bees usually have emotions, typically have friends, either can be extroverted, introverted, can be born in the year.
Just stop.
Yeah. It's kind of cool because like if you think about like say like the Chinese calendar, it's got like the 12-year cycle with all the different animals. It reminds me of it because it's 12, like characters, like mythological characters, and they all have personalities. And if you think about that and compare it to astrology, it's almost like a pre-scientific form of psychiatry or psychology. Because we all know, people are all we're all unique snowflakes, and we're all special and stuff. Cameron has 40,000 pets. That's awesome. And if you can kind of like distill personality types into characters and make it part of your culture, that's kind of what that sounds like to me. You just it was unfortunate that it got connected to astronomy. Yeah. Yeah, so
Press
yeah.
the teacher.png, Mr. Estes.
Oh, I didn't see that. Click to download. You're giving me a virus.
No.
Yeah. Oh my gosh. So something that I don't know if it's happened yet. I don't know, but if it hasn't happened yet, I'm not sure why. There are so many pictures of me in ridiculous teachery poses on YouTube now. It seems like there'd be more of those by now. What are the characteristics of a Capricorn?
Everybody's saying, "Oh yeah, he's a good Capricorn person."
Yeah, I don't know. There is this great experiment that was, I don't know if it's an experiment that was done about horoscopes. So
I got a question.
Go ahead.
So if you were born on a leap year, would you have a zodiac sign?
Oh yeah, you would. I think that the windows are flexible enough that one day isn't going to matter. So yeah, you'd still have a zodiac sign. Should you grow out your mustache? I would say not.
You don't have any.
Hold on. As soon as I read that, I just remembered what was going on my face in 8th grade. It was going on. Tell you what, there's no better time than quarantine in the summer, man. There's no better time. Yeah. High school facial hair is a whole thing. Anyway, no.
Mr. Estes, I have a question.
Go ahead.
Do we still need our dirt?
No.
Because my stepmom threw it out yesterday.
I still have the dirt.
There is, I don't know if it's been sent out yet, but there's like gonna be some list published about like materials to return to school, I think on like June 8th or so. Don't take that date from me, but it's something where you have to bring all your textbooks and stuff. Yeah, we do need those plastic containers and the pipettes back. Clean them, please, because it's gonna be like 40 containers for you guys. But yeah, my original thought was I thought we were gonna be out of school for like 2 weeks, and that when we came back, we'd all have dirt. We could look at it under microscopes. Yeah, that's not happening. So the other option that I had was, I've got a microscope at home, but like it's honestly not very good. So I thought maybe I can like put it underneath and just send pictures, but it's awful. Yeah.
Look at David under a microscope.
Sorry, what?
Never mind.
Oh, okay. Yeah, this microscope is, the optics are just not very good. Anyway, what else was I don't remember what we were talking about. If we were talking about anything. Oh well. So this is an earth science class. We're talking about the solar system. What do you guys ever like watch flat earth videos?
I
Nah.
watched Logan Paul. He proves the Earth is flat. I'm kidding.
Yeah, I have. I remember that when that was a thing. But I think he was trolling them, wasn't he?
I don't know what's up with that guy. All right.
I'm pretty sure he was, or at least.
I thought he was dead.
I thought he was dead. I
Yeah.
want to say a really, really dark joke.
Well,
Yeah, but I'm not gonna say it.
Well,
Logan Paul's poopy head.
yeah,
I don't like him.
yeah. There's
The
so
Earth is a cube.
much nonsense with flat Earth, but that honestly that's kind of been important just for me as a teacher, because like one thing that I think, being like a person who likes science, to see people get it so wrong, I'm like, no. But on the other hand, one thing that always, it's the question every science teacher gets is, why are we learning this? And sometimes, teachers have to make up a stupid answer for that. But it's usually because science is irrelevant to people's daily lives. But when you have a whole bunch of morons saying that the Earth is flat and making it a big public deal, all of a sudden, yay, it's relevant how to do science properly and like how to show that they're doing it wrong.
This is what the Earth really looks like. Hold on, let me go to my downloads.
Yeah, Annika, you're right. Planets do have astrological meanings.
All right, there you go. That's what the Earth really looks like.
Boy.
This is dinosaur.
That's good. That's good. Oh man.
I always showed you the picture of dinosaur Earth.
Yep, that is
Dinosaur Earth.
a good one. All right, well, we are now like more than 10 minutes out. I've got another class later and also lunch.
Do you like my back screen?
Oops.
No,
It was the fall of the
Mr.
Soviet Union.
Mr. Estes, I have one last question.
Go ahead.
So I've looked up pictures of Mercury in the past, and it often comes up with like a bunch of different looking pictures of the same planet. Like sometimes it's like brown and purple and super sparkly, and then other times it looks like the moon. So
yeah, let me answer that. So this actually kind of plays into flat Earth because of how images of space are taken. So there are what are called optical telescopes, which are the kind, like with lenses that you can look through. And those pictures look like what it would be like if you were to just look at it with your eyes. Thing is, a lot of things are invisible to our eyes that are actually interesting to scientists. For example, if you were to look at, Jupiter with a radio telescope, it would look like this huge blob because what it would be seeing is the magnetic field. And you know that if you were to look at a temperature map of the Earth, it would mostly be warm around the equator and cold around the poles. Depending on what you're looking at, the picture will look different, but if it's invisible light, right? So let's say you wanted to take a picture of Venus. If you just took an optical picture of Venus, you're going to see the clouds, and that's it, because that's all you can see. But what if you want to take a picture of the surface of Venus? You're going to need to use a wavelength of light that can go through the clouds. We use that on the Earth to predict the weather, Super Doppler 8 radar. You're just using a radar telescope to look at the air, and you can see through the clouds. Well, if you wanted to map the surface of Venus, you'd want to use radar. But radar doesn't have a color. So when you take a picture with radar, it's black and white. That doesn't look good, so you color it. It's called a false color image. If you were to take a picture of Mercury with an optical telescope, you're going to have some imaging problems One, because of the limitations of visible light across great distances, but also because you've only got the light of the sun. Another way to get an image of Mercury would be kind of like a sonar image. You know how like sonar images work with like submarines and stuff. So let's say you got a satellite in orbit, it bounces off a radio, it like sends a radio wave to the surface and then maps the reflection. That picture isn't what it looks like. It's more like a sonar map. So what the scientists at NASA will do is they'll take that and they'll just process it to make it look cool. Sometimes they're color coded where like, you know, red is a high altitude and purple is a low altitude. And so they'll look like a crazy rainbow picture. Other times they'll just colorize it to make it look kind of like rocks to match our expectations. So what does Mercury actually look like? I think it actually looks like our moon, like white and gray, or probably mostly gray and brown. But if you see a picture that has different colors, it's probably just because it was like a radio image that was colorized to match our expectations. Just about any picture of a nebula that you see, all those bright colors, those are all fake. Nebulas just look white. The reason that they have those colors is because they're taken, it's a composite picture and they're colorized so that you can tell what's going on. I don't want to use the word fake. Maybe it's synthetic.
Check the image I sent.
Yeah. Anyway, I'm gonna go now. It was super.
Check the image first.
Check the image for. Oh, did you send out another one?
Yes.
Is that FSFF?
Yes.
Why do I always have this fear in my stomach before I open a picture from you, David?
That's my job to inflict fear.
So, my
The Earth just spins really fast. That's why it looks like a spear.
mm-hmm. My daughters are 5 and 6, and my older daughter, especially Riley, she loves animals and she really likes dinosaurs. And every once in a while, she'll just kind of like, you know how kids just say what's on their mind. She'll just like say like how sad she is that the dinosaurs died. And sometimes when she's playing a game with her sister, they'll like be playing dinosaurs, and the goal of the game is to dodge the asteroid. Like as if, you know, she doesn't get that like the asteroid hit the planet and like destroyed the environment and that caused the extinctions. She thinks that like the asteroid like shot them. But anyway, thanks for the memes. Thanks for the chat. It's good talking with you. Anyway, look for the video tomorrow. I'll post it today so you can do it early. It's all about the phases of the moon. It's been real, y'all.
So so we don't have any assignments?
Nope, no, nothing for today. I used it up yesterday because yesterday's lesson was just so terrible. Anyway, see ya.